Number 38 from the book Segel is the series of preparation of the buffer. So you are given the sum of the chemicals and you have to make the phosphate buffer, 40 liters of 0.02 molar. So at the series of, for the part A, part D, and part J, so you are given different kinds of chemicals and we need to make the buffer out from what you are given. So part A, you have 2 molar of H3PO4 and KOH1 normal. So to prepare the buffer, let's imagine that you have one beaker and you have to make the phosphate buffer in this beaker 40 liters. So you might imagine that first you have to calculate the volume of H3PO4 that you're going to put there. And then you also need another component of KOH. And then if these two addition is not reached 40 liters yet, you also need to top up with water to reach 40 liters. So first, I would begin with find the amount of H3PO4 that you need to prepare into the beaker. So the phosphate buffer of 40 liters of 0.02 molar or the phosphate ion will only come from H3PO4. So you need to calculate the mole of phosphate in the solution that you need. So you would like to prepare 40 liters of 0.02 molar of phosphate buffer. And this, when you calculate the mole, you will have 0.8 mole. So you need 0.8 mole of phosphate. And since we have 2 molar of H3PO4, so you calculate the amount of H3PO4 that you need to add into the beaker. Because what you want is, you want 8 mole, but you have 2 molar. So you can calculate the volume of H3PO4 by dividing the moles 0.8 by the concentration molar. So this will give you 0.4 liter. So this is actually the first component, H3PO4, that need to be added into the beaker, 0.4 liters. Next step is to find the amount of KOH that you're going to add. So next step, to find the amount of KOH. So to find the amount of KOH, you need to working on how much of hydroxide ion you need to put in order to change, raise the pH into pH 6.9. So first, you have to understand how phosphoric acid being protonate. So this equation shows you how phosphoric acid protonate and give its proton. So because we starting from H3PO4, so if the equation doesn't give you the pH of H3PO4 that you're starting with, we assume that what you are given is very, very acidic. So the pH of H3PO4 right now might be even less than 1 or less than 1. So you starting from H3PO4, but you need to raise the pH into pH equal 6.9. So first, if you follow by this protonation process, you will need to change the H3PO4 into H2PO4 minus, and then to raise the pH up until 6.9, you have to maybe partially change H2PO4 minus into HPO4 2 minus. Because let's focus at the pH 6.9 here. So pH 6.9 here, at this condition, the solution will contain either H2PO4 minus and HPO4 2 minus. So you can see that we have two steps here. So at step 1, you have to change H3PO4 to H2PO4 minus. And at step 2, you have to partially change H2PO4 minus further to HPO4 2 minus. At step 1, as we say that H3PO4 is needed to be changed into H2PO4 minus. So, of course, we need hydroxide ion to change H3PO4 to H2PO4 minus. And this hydroxide ion is come from KOH, right? So again, at this step 1, since we said that we begin from H3PO4, very, very acidic. So at that point, 100% of the solution is in H3PO4 form. So we have to change 100% or one equivalent of H3PO4 into one equivalent of H2PO4 minus. So that's why if you need to change one H3PO4 into one H2PO4 minus, this is just how you balance the equations. It means that you also need one equivalence of hydroxide ion in this reaction, right? So that is the first step. But for the second step, the beginning of the second step is when you have 100% or one equivalence of H2PO4 minus. But to change or to raise the pH into 6.9, we need to use the Henderson-Hasselbalch equation to calculate the amount of the hydroxide ion that you need to change H2PO4 into HPO4. So pH is 6.9. pKa will use the pKa that closest, the most closest to what we want. So in this case is 7.21. And then log B over A. So B over A here will tell you the ratio of either H2PO4 and HPO4 at pH 6.9. So your job is to calculate each ratio here. So now I would like to show you how to solve for the ratio B and A. So since we have 6.9 as pH and 7.21 as pKa, so first you will get log B over A equal minus 0.31. And then you can take the entire log to solve for B over A will be equal 0.49. So now to solve for B or A, you have to change some of the parameters here. Since we know that all we talk about right now is the equivalence, so A plus B will equal one equivalence or equal 100%. So if you want to solve for B, you have to change A parameter in terms of B. So A will be equal 1 minus B from the equation that we talk about right here. So what B divided by 1 over B, sorry, B divided by 1 minus B will equal to 0.49. And then B will equal to 0.49 minus 0.49B. So that means 1.49B equals 0.49. This is just how you solve for move to the other side of the equations. So B, it will be 0.049, sorry, 0.49 divided by 1.49. And that is equal 0.33 here. So as we solve for B, we can solve for A using the 1 minus B here. So A will be equal 1 minus 0.33 equal 0.67, right? So right now at pH 6.9, we know that our H2PO4 minus will have 0.67 equivalents, while HPO4 2 minus will be only 0.33 equivalents. So since we said that at the starting of step 2, here, you're starting from 1 equivalence of H2PO4, but at pH 6.9, it had to be partially changed into HPO4. And right now from the calculations, we know that it actually need to change into HPO4 2 minus 0.33 equivalents. So if you want to make 0.33 equivalents of HPO4 2 minus, it means that you need 0.33 H2PO4 to be react with hydroxide ion 0.33 to make 0.33 HPO4 2 minus here. So for this step, we need 0.33 equivalents of hydroxide ion. So the total amount of hydroxide ion that you need to raise the pH into 6.9 is the total from step 1 and step 2 here. So total equivalence of hydroxide ion will be equal 1 plus 0.33. And this is 1.33 equivalents. So this is equivalence. It's not moles, it's not molarity, it's not volume. So you need to change equivalence into moles. And then we're gonna know that how many moles of hydroxide ion we need to add into the beaker. And then we can calculate the volume of KOH from what we need. So to calculate the moles of the hydroxide ion, you need to take the equivalence and then you time by the moles of the phosphate buffer, because this we're comparing back to phosphate, right? We're comparing back to the moles of H3PO4. So that's why we use 0.8 moles of H3PO4 here. And that will be equal 1.064 mole. So now we know that the hydroxide that we need to be 1.064 mole. So 1.064 moles OH will come from KOH, and our KOH is 1 normal. So you can calculate the volume of KOH by using the amount of mole that we need divided by the concentration, which is 1 normal here, and so we get 1.064 liters. So normal is, is actually similar to molar, and then when we calculate it, we'll get the unit of liters as the volume. So for the final answer of the volume of KOH, you need 1.064 liter. So to sum up, when you have the beaker, the first one, you have to add H3PO4. And we already calculated which equal 0.4 liter. And then next, you need to add KOH, and that is equal 1.064 liters. And then since we need to prepare 40 liters of phosphate buffer, so that's why the last part here, you need to top up with water to reach 40 liters, right? So top up water to reach 40 liters. So the answer for these questions is have to mention all three components here, H3PO4, KOH, and water to reach 40 liters. I would like to explain more about the tip of the step 2 of hydroxide part. Some of you might ask that, how would we know to calculate or to use which ratio, either A or B? So in this case, you change from H2PO4 minus to HPO42 minus, and you know that you need to use the hydroxide ion to change H2PO4 minus to HPO42 minus. And then the amount of hydroxide ion will only depends on the amount of HPO42 minus that you want at pH 6.9. So that's why we say that we need to use the ratio B in order to calculate the equivalence of hydroxide ion here. So that is the first tip. So you don't need to calculate both A or B. Sorry, you don't need to calculate A and B. You can just focusing on only one ratio to work on. And that is the tip for knowing which ratio to calculate for the equivalence of hydroxide ion. So let me know if you have questions about these solutions. Thank you.